So let's get started. So I'm really happy to be here. So my name is Farid Medjdoub from IML, the lab that you can see here. So this belongs to the French government called CNRS. And it's located actually 1 hour away from here, so quite close to University of Ghent. So again, thanks for the invitation to the organizers. I will start the first half, will be probably for expert in the room, will be just reminders, I guess. So why gallium nitride for high power, some basics, with quick device fabrication, and some past and maybe also some current challenges of lateral GaN amps. And then I will move also a few slides to some new device design, some exciting projects for high power, moving to vertical, for example, and a new material. Okay, so just some quick words. I think we had a nice first talk, so you have a flavor of the importance of power electronics. So this was focused on silicon carbide, but just general words here, just to say that this is a very large topic, interdisciplinary nature, involving, as you see here, many different topics. So the power electronics is currently one of the most active disciplines in electric power engineering. So this is used almost everywhere in modern society, and this will ramp up, increase even more in the next future. With the electrical vehicles, for example, we had a nice example. But there are many others. So it's not just automotive, even though it's obviously a huge part of the story. But you have many other applications where you can use. This is just categorized by power and versus frequency here. Of course, I don't go through any details here, but you can imagine that impacts a little bit of everything. Let's say. Okay, so what is an ideal power switch? What you would like is, so we're gonna dig deeper into the technology here, so it's less the module level, so it's quite complementary with the first speaker. So we'll go into inside the device, let's say. So so what is an ideal device? In the off state, this should block the high voltage with no leakage current, so as low as possible. The on state, no resistance, obviously it's kind of impossible, but you want to be as close as possible to the lowest resistance as possible, and also mentioned in the first talk is the switching from on to off and vice versa. This should happen as fast as possible with no hysteresis, no memory effect, no charge storage. Okay, and I think we all agree here that this may be enabled by new material properties. Let's say get closer to these features here, novel device concepts. That enable new system solutions. So if you look at from, let's say, an overall perspective, so what should be improved to achieve better power switching? So at the system level, we heard about it, this nice silicon carbide. This is the strength, by the way, of silicon carbide. Outside the cost, of course, is the thermal dissipation. So you definitely benefit from fewer cooling needs, smaller filters, passive elements. This enable, let's say, smaller system size and weight reduction. That's one of the strong requirements. At the module level, you want low losses, you want to increase the efficiency and high switching efficiency. This one is also important, that impacts directly the size of the system here, with no recovery time during switching. And this comes down somehow to the higher junction temperature, and also important point is the electron mobility here. Okay? So that's in turn explain you why this wide bandgap that has better features here are much more interested in silicon in this way. So just some quick words. I don't think I need to spend much time. I think most of you are expert in the field, so these are very simple equations here. So the figure of merit are quite simple. So if you want to minimize the on resistance to the first order and block the voltage to a certain voltage, and this depends on the electron velocity. So that's why this charge mobility is very important, and the current density. And for the breakdown, you want higher critical electric field and higher energy gap. That's what this simple equation tells you. So of course, we shouldn't forget that silicon is a wonderful technology. So we have this very nice super junctions as a reminder for some newcomers. Let's say there was for a long time planar MOSFETs here, and this works very nicely for a while. But the problem is the higher voltage requires thicker drift layer here. So you have a strong trade-off between the on resistance and the blocking voltage here. So people have been very clever to implement this super junction. So this is basically multiple vertical PN junction here that are implemented, and you end up with a much higher resistivity ratio as compared to this one. And you kind of overcome the trade-off between the on resistance and the breakdown voltage here. So question is how far you can go with this super junction concept here. Obviously, you can see this is an example from a well-known company here that you recognize, and you see that it's improving over time, which makes sense. But then you also reach at some points the intrinsic properties of the silicon, the material. So this cannot be improved forever, let's say. And if you look at here, some initial, this is 2018, before 2020, these are quite immature and initial silicon carbide and GaN devices, and they're already better than best-in-class silicon superjunction devices. So this will improve significantly also over time. So you can feel the interest, let's say, of using new materials, if of course reliability and all the other requirements are fulfilled. So this is the desired corner again for the newcomers here. So you want to reduce the on resistance and increase the breakdown voltage as silicon limits, the intrinsic silicon limits. It cannot be overcome, let's say, indefinitely. That's just what I was saying here. And new material, you can see some example here. Of course, there's gallium nitride and silicon carbide. Silicon carbide is happening now. Gallium nitride hopefully will ramp up as well. And you have some other material that will give some words at the end, so you have gallium oxide. People, you can argue that about diamond, looking at the size and price. There's a nice also aluminum nitride, which is reaching 4-inch currently, and is interesting, let's say, long-term technology here. Okay, so this is the spider that that everybody's using. So again, I don't need to spend too much time, so that proves or that reflects the interest of the wide band gaps. So you see the advantage in electric field, which is a key parameter here due to the band gap, but of course the velocity, both for silicon carbide and gallium nitride as compared to the silicon one. And very important is the thermal conductivity, which is not really an asset for gallium nitride. That's also something to keep in mind. But for silicon carbide, definitely, and for people who have some doubts about the importance of this thermal dissipation, I guess everybody experienced at some points, the overheat in his phone, especially during summer. So, you want to integrate some devices in a small box. This happens if, you don't have a material that dissipates the heat properly. So even in commercialized system, that still happens. Okay, so why gallium nitride then? So there's a significant advantage in terms of high frequency operation. I'm not talking about RF devices, which is definitely obvious. There's no other way. If gallium nitride can be used at this frequency, this will be gallium nitride. In this case, of course, you have some very strong contenders, let's say. But if you look at multiple megahertz, I think there's nothing that matches gallium nitride today. Okay, so probably this is just for some specific applications, but from technical point of view, that's a fact. Okay, so you can see just an example. That's an old one here. Efficiency versus power at this frequency here. And another key feature is the reverse recovery charge test here. This is also an old example between a silicon MOSFET versus a GaN. And you see that GaN nitride offers advantages of power density, efficiency, hard switching with continuous use of the reverse characteristic at very high frequency. So we are talking about more than a fold drop of this recovery charge here. And that allows you actually to have much smaller devices. This is on the market, that's nothing new. You can see you can have very small, powerful chargers here. So smaller, lighter, with high power density. So that was the key point of this wideband at low voltage range, let's say. So what's the situation today? We have to be also realistic, not oversell, wideband gaps and say it's gonna happen, but today is still, dominated by silicon. Obviously, silicon carbide is now taking part of, especially for automotives, taking part of the market here. This is the definitely preferred choice at high temperature, for high temperature application. But you also have to say that that silicon and also silicon carbide cannot compete in high frequency range. So we could imagine that can play an important role in this frame for high voltage, combining high frequency also. So there is at least a niche for gallium nitride here, and there's some other debates about the automotive application, but probably we will further discuss that later. Okay, so this next part is just some basics about gallium nitride. So what is heterostructure? This is just a very simple band diagram here. So you can see that the 2-leg is located at the Fermi level above, the Fermi level above the condition band here. At the hetero interface between GaN and gallium nitride here. So you have a collection of electrons that are confined in a triangular quantum well, resulting from both spontaneous and piezo polarization. And the key feature here is nothing is doped here. Nothing needs to be doped here. So that's really an important point here. So as a follow-up here, that explains you to a large extent why you can get lower on resistance with gallium nitride. Is mainly due to this 2-leg density, which is pretty high. In this case, it's a bit lower than 10 to the 13, but it can be 10 to the 13, depending on the aluminum content and how the barrier is designed. Here, so you can have high electron density and combined with high mobility. We're talking about 2,000 centimeters square per second. And because of his wide band gap, 3.4 eV, you have obviously high breakdown, and the n-doped nature of this material provides you low capacitances. There's no junction to deplete here. So, so again, just as a wrap-up, you don't need any doping for device operation. You have high 2-leg concentration that depends on spontaneous and piezo, so it's quite, let's say, inherent or natural, let's say, to the material. So piezo is related to strain, and this is the different band conduction here. And the electron density is controlled by the charge induced by the gate. So you can basically fully deplete with the gate, the channel here, and get nice transistors. So that's the concept here. Of course, you have some dark sides. Nothing is pink, let's say, beautiful. There's also some drawbacks here. So you have some inherent, let's say, surface charges here, that may cause 2-leg depletion. So it's like virtual gate. So you control this gate electrode, but you have kind of a second gate electrode that you don't control, and that depletes also the channel. So this is the so-called current collapse here, that are negatively charged here. Obviously, this problem is well known, and this has been solved for a while with proper pre-treatment and passivations, and also from growth point of view. How do you terminate, let's say, the growth and things like that. So this is, let's say, to a large extent, quite solved. Yeah, we had heard a nice discussion about substrate previously, which I completely agree with. So one of the questions is, if you use gallium nitride, which substrate should you use for GaN? So obviously, you want to use GaN on GaN. Zero lattice mismatch, thermal mismatch. That would be the best, let's say. This is available, but as mentioned previously, the cost is really prohibitive. So, and also the size, even though they are, keeping improving. So this is not a short-term technology, let's say. Silicon carbide, it's always there as a substrate in this case. Beautiful substrate. This is the mainstream in RF devices. Definitely, GaN on silicon is just for some of the application, but if you want high power in the gigahertz plus range, you want to use this one, GaN on silicon carbide. Sapphire is not really an option. I'm not aware of outside the optoelectronics. I'm not aware for power that the thermal dissipation is so poor that it's very difficult to be used. And though some people claim the opposite, some companies, but my opinion is it's gonna be difficult to the thermal penalty will be too high, let's say. And of course, there's always silicon that brings you the cost lower, and although technically more challenging, I think the previous speaker just said that the cost is the driving force for power devices, much more than RF, by the way. And that's why it can only happen on silicon, let's say. Never say never, but let's put it this way. If you can do it on silicon, that will happen on silicon. Of course, with all the requirements. And if you use something else, it's because it doesn't work on silicon, basically. That's the point here. Okay. Those numbers are probably wrong now. This is an old slide, so don't jump on me, let's say. So, but just to tell you, I think it has been shown also by Bosch previously. Obviously, everybody knows silicon carbide is expensive. Obviously, it's not 4-inch anymore. Looking at Peter, it's going to get crazy. It's getting to 8-inch now. But still, I mean, it's much more expensive, than silicon substrate. And important point here is the cost of the substrate. There's also the cost of fabrication. And the beauty of using GaN on silicon is you have access to existing fabs that you don't need to really, tune, let's say, or upgrade. So fully depreciated fabs side by side. So most of the things are compatible. Of course, there's always things to be changed, but you basically don't need to invest billions, creating new fabs. So that was also one of the advantage here, and the integration possible with silicon CMOS that some of the people are working on. Okay, some quick words about fabrications for people who are not familiar to the device fabrication, or for people working at the system level, for example. But you probably all know that you start with some specification, what your customer, the company wants, then you design that allows to generate a mask layout. Once the mask layout is fabricated, you start the fabrication clean room. Of the chips, and there's a packaging backend. Of course, this is just a very small drawing just to tell you that there's a loop, and usually there's several reverse engineering after, many iteration to improve, all the parameters and the performance reliability balance here. So where is the clean room here? Just some few pictures quickly here. So this is a fully controlled environment here. So this is control of what I mean by control is contamination, humidity, temperature, pressure, a little bit of everything. And again, for people who are not aware, this is up to 1 million times less particle than outside. So that's quite a well-controlled environment. Of course, you have different classes of clean room. Don't go through here. Different ISO class. Just to give you some example here. So real foundry is class 1. There's no human presence. It's everything automated, even this very large 8-inch wafer or even more. In our lab, we have 1,600 square meters clean room. It's a class 1,000. It's manual operator, so people are doing their own lithography themselves. But that still allows achieving, demonstrated prototypes and helps, especially companies to let's say, guide some and give some direction about what to use in their foundry. And it's much cheaper than doing, using this very expensive thing. So I think it's a good trade-off, people can work together and get things done faster. Yeah, again, here I don't go through. I want to keep some time for the more exciting stuff. This is just a list of, I don't know if you get the slides at some points, probably yes. And so you can have a look of the major steps, let's say, that you can use to produce devices. This is an 8-inch example here. And just a quick picture of how, it's just an example, of course, this is not generic at all. That's just, it's probably even an RF device here. I'm not sure it's an RF device. But whatever, you can see the contacts here. This is a T-gate, some very large field plate here, the drain contact. That's a lateral GaN head here, just to give you an example of a cross-section of a real device. Okay, so let's move to some of the challenges that most of them have been solved for lateral devices. So just some quick general targets. So this work has started, I think we worked on that close to 20 years ago. For power is probably 15 years ago, something like that. So the target was the 600 volt node, 1200 volts. So obviously this is reached by many companies. We'll come back to that. 1200 volt is another animal, let's say. So you want low on resistance, as we discussed. You want also this low dynamic on resistance. Come back to this point. And normally off operation for safety. So means a threshold voltage well beyond 1 volt. So this has been also a struggle at some points with large gate voltage swing. Okay, so that are the main and general requirements. And for people who have worked on in this field for a while, they know that the dynamic losses actually was the one to be overcome. This was really the real challenge. And I explained what it is in a couple of slides here. So what is the current collapse? So you have a static on resistance, and what happens is the device changes properties depending on the history of biasing. So you bias the device, you kind of stress the device, you remove your own resistance, and that's not the same. So obviously that's not what you want. And the effect is a reduction of the current density, which is linked to the increase of on resistance. And you can also have, in some cases, depending on the origin of the problem, you can also have a shift of pinch-off or increase of leakage. This really, the recovery, because these are memory effect, and the recovery can take minutes, depending on the time constant of your traps, hours or days. And I think everybody, working on in this field for a while, have seen that, okay? Because things were not really well understood at that time. And again, this depends on the bias condition, and this impacts, as you can imagine, the switching properties and the safe operating area and so on. So that's definitely not what you want. And just to give you a nice example from our colleague, KDT JU, Padova. This was about 10 years ago. You see, it's a long time problem here. Carbon is now well mastered and well known, well identifies the problem as a source of trapping. We've done the same for RF devices, by the way. So this is I come back also to the anomaly of P-GaN gate. I will describe that later. So the important point here is they compared the highly doped buffer GaN versus a doped buffer GaN with an GaN back barrier here, about half a micron, and a double hedge junction with no doping, with no carbon. And you see the results here of the on-resistance transient versus time here. And you see that the high carbon, let's say, guy here is delivering very high current collapse or huge increase of the on-resistance and recovery after a while, which is less pronounced in the case of when you put away, let's say, the carbon from the 2-day, and if you get rid of the carbon, there's almost no recovery and no trap. So it's a nice way to identify the carbon to blame the carbon as the source of the current collapse here. So those things are also well understood. So now there are some modern buffer. I'll show you an example also later of very nice buffer that provides you enhanced, let's say, breakdown voltage with low trapping. So this is now also mastered today. But that was one of the early problems, and also carbon was. So you can use carbon, but you have to use it with the right concentration and the right location. That was the message here. Of course, leakage, you can have, it's very busy, these slides, there are many ways to get leakage. You can arc, you can go through the substrate, you can, depending on the defects from the growth, you can have punch through. So there are many ways to get leakage. Those things also people spend time, and many groups work to solve each of those leakage issue, and that was also obviously critical for reliability. So another issue that people have is to make this device normally off, because they are naturally normally on. So you have a negative threshold voltage, so you pinch off negatively to really deplete fully the channel. So you have to do something, to make it normally off, and having a threshold voltage well beyond 1 volt. So the first thing you can think about is just recess all the way to the buffer. And the dielectric is a kind of GaN MOSFET. Many people have worked on that. So you fully recess the barrier. So the advantage is definitely you get high threshold voltage. That works very nicely. The leakage is also low because you have a dielectric here, which protect the gate. And you also can have large gate voltage swings. So paper DC, it works. Disadvantage is trapping. This has never been solved here between whatever it's an oxide or let's say a gate dielectric. This has never really been solved up to now, let's say. And obviously the peak electric field just cross this sensitive region here. And again, an example here of what you can get with a mishand. In this case, it was an aluminum oxide, silicon nitride that has been used below the gate. And you see the effect of stressing the device here. And the threshold voltage is keeping shifting. So there's a significant shift of threshold voltage due to injection of electron from the to the gate dielectrics here. And again, I'm not aware that anybody has solved that so far. Let's say, especially up to the industry requirement levels. So that's some other approaches, like the implantation. So there was many papers on fluorine implant that you may have seen in the literature. I just put a cross here that not really working. Again, this works perfectly. You can shift, you can even fix, you can fix the threshold where you want, depending on the dose that you use with fluorine. So that works very nicely. I think we've done that at IME 15 years ago or something. So this works very nicely, but the problem is it's highly unstable. And to make it stable, I don't think, there was some claims, but I don't think anybody really fixed the problem of stability of this fluorine under hard switch, under real temperature, stress, and so on. So that was not an option. And this P-GaN, having a PN junction here, this was the best solution so far. That's what most of the people, it's not the only one, of course, but that's what many people are using. So you basically can show you the quick process here. You grow a P-GaN, of course, that's different design here of the aluminum content, of the magnesium concentration, of course. So I won't come into this detail, but you have a good combination that provides you a high threshold voltage, so you edge your way except below the gate. That allows you to form the source and drain ohmic contacts. And here, of course, you isolate the devices and then you align the gate, on top of the P remaining layer. So we have to mention that this is not a trivial solution. So the ICP etching here, as you can see, there's very poor selectivity between the P-GaN and the I-GaN. So it's very tricky because you cannot etch too much of your barrier. You don't want to etch your barrier at all. Otherwise, you impact, the on resistance and the two-day. So you have to be very accurate, the nanometer scale, knowing that this is quite thick, between 50 and 100 nanometer, let's say, and you have to end up, let's say, at a couple of nanometer accuracy with poor selectivity. So that's a tricky process, but people manage to do that even at the foundry level. So this is just some pictures of the device. So you have to align the gate on the PGAN. That's something I mentioned already. Yeah, just an example of misalignment. People never show bad things, so it's good sometimes, to show that things are not working. So this is just, you see here, if you look at carefully, there's a PGAN here that you can see, and the gate, the metal, the large stuff here is overlapping a little bit, outside the PGAN. And the result is here. Actually, you have a double modulation, and you have a negative threshold voltage here. So you have to be careful, with that. And that also somehow highlight the effect of this PGAN layer. And if you're inside and properly aligned, you get nice normally off. Of course, you can get even higher threshold voltage depending on the active layer design. Here's just about 1 volt in this case, or 1.5, but this can be further tuned. But of course, nothing is perfect. So these are our friends from Padova again here. They did some step stress on some devices, and what they found is it's pretty reliable. But if you go to large gate voltage swing, let's say above 5 volts, probably 7 volt plus, you find some time-dependent degradation. So there's a limit to the voltage swing, so it's not like super large, but people probably live with that and keep improving also this feature here. And maybe a last normally of design that I can discuss here is the cascode here. Again, works very nice on papers, not on paper, but also experimentally. So you combine a GaN hand with a silicon MOSFET here, and the silicon device, normally off, provides the normally off function, while the GaN, normally on, very robust, turns on as soon as the potential across the silicon MOSFET is below the threshold. So that works very nicely. So you end up overall with a nice normally off, with low leakage and all the things you need. So some people are using that also, let's say almost commercially, probably. So there are some disadvantages. So the message here is you don't benefit fully from gallium nitride. So you always prefer intrinsic normally off. So the driver sees silicon MOSFETs. So you're limiting temperature, for example. So you go back to the limitations, basically, of silicon somehow. Okay, and also in terms of instability, dynamic instabilities, this is not trivial. So that's probably the SOA is more restrictive in this case. Okay, but some people are using them. So I move now to always talking about the challenges and how to push further those lateral devices. So let's get some words about breakdown voltage. That was also kind of limitation. It's not trivial to grow on silicon, and to grow thick on silicon is even more difficult. It looks easy now, but people struggle for years. So how does it work, the breakdown? So you see just, it's dependent, of course, on the gate to drain distance here. So if this is quite short, you have a huge electric field peak here. So you break down the vicinity of the gate, let's say. So you have a bad example here with a 2 micron. And then if you increase, so you have the depletion here. So if you increase the gate drain distance, you enlarge the space charge region if your buffer layers are thick enough. And that allows you to increase the breakdown voltage. But regardless of your buffer thickness, at some points, you will get saturation here for any given structure. Of course, the level of breakdown and the gauge drain where the breakdown will saturate depends on the quality, on the thickness, and all this thing. But basically, this will always look like this. Again, this is an old bad example. Don't be afraid. It's just to give you especially this flavor here of what happened on silicon. So you understood that the limitation is the silicon itself. And if the gallium nitride growth is good enough, that's the only limitation of breakdown. And of course, if the gauge drain is large enough, let's say 10 to 15 micron, for example. Okay. So, yeah, that's what I was mentioning here. So for large gauge drain, let's say beyond 10 micron, let's put it this way, So you are limited by the parasitic conduction here. And actually, we showed that a long time ago at IMEC, at my time there. So we showed physically the breakdown, between a short gate drain distance here. That happened, you see, you have the silicon substrate here, and you are really breaking down in the bulk in the buffer layer, sorry. Okay, so the catastrophic breakdown is here. That's what you see. So these are real cross-section. And another one with large gate drain distance, where you really break down through the substrate. So your substrate ends up here. So you have a physical proof of the breakdown mechanism, let's say. Okay. So how to further push the breakdown? So people worked for a while on that. So obviously you want to improve your buffer layer and the thickness of this buffer, but keeping in mind also current collapse. So it's not just increasing the breakdown, it's also increasing the breakdown while maintaining low current collapse. So it has to go together, not just increasing the breakdown. So many solutions have been, I cannot go through that, as based on carbon doping, iron, YESvGaN, step graded. I'll just show you one example here of what is a kind of state-of-the-art technology here. And also keeping in mind that whatever you use, there will be a limit of, I put 6 micron, this can be discussed, but if it's too thick on large diameter, that's not gonna work anymore. You're gonna get defects and the strain becomes dominant and so on. So the thickness will be limited anyway. So just a quick example, I think this has been drawn by Soitec, the logo is missing, sorry about that, but I can mention it here. So this is an old solution based on step graded combined with carbon. So step graded means high aluminum, you start with aluminum nitride as anybody, and then you go with high aluminum content with certain thickness and you decrease the aluminum content by step. That's why it's called step graded. And you end up with a GaN channel, and there's some carbon doping here at some location. And on the right, this one is a superlattice based. So the idea here is put some pairs of aluminum nitride, gallium nitride. It can be YESvGaN, by the way, but in this case it's aluminum nitride. So many pairs of aluminum nitride, and the core idea is to maintain this high aluminum content, to below the critical value, which is in the case of aluminum nitride is a couple of nanometer. So you can see all the layers stacked here, and this gives you, in this case, 3.7 plus the carbon dot region that is away from the 2D. And you want to get the best of both worlds with an increased quality. So let's see what we got. So in terms of breakdown, keep in mind this was a little bit thicker, so slight improvement above 1 kilovolt here in the case of superlattice as compared to the reference. In terms of temperature, also there's a slight improvement. It's not tremendous, let's say, but the behavior versus temperature was pretty clean. But more important is you can reach high breakdown, but also low current collapse. So the way it's measured here, it's very simple. So you just probe vertically the buffer. This is called a substrate ramp. So you go just back and forth and look at hysteresis to see if there's any memory effect. Some people try to know the location. I'm not convinced about the fact that you can really know the location with this technique, but that's another debate. But at least you can see if you have electron trapping or not. So this reference was designed for 600 volts, and you can see you go back and forth from bottom to the top with a certain switching. We tried different we tried different sweep rates here, and you see that the hysteresis is very low. And if you go beyond the specification, in this case 800 volt, you start to see hysteresis in some cases. And if you keep increasing the voltage of the substrate, 900 volt, the hysteresis is just huge. Okay, but that's expected because you activate the traps, and that was that was devices for 600 volt in this case. If you do that with superlattice, that's really amazing. You can see that you can drive the device well above, at least the buffer, well above 1 kilovolt without seeing any trapping, or very low hysteresis, let's put it this way. Okay, so you can get high breakdown voltage and maintaining low current collapse if you design properly the buffer layer. Okay, so we played with it. We added Soitec logo is here this time. They did a PGAN based layer based on this nice super lattice buffer, and the idea was just verify that in a normally off condition, this nice buffer layer, and that works pretty nicely. You can see the floating grounded substrate breakdown here. So the floating is well above 2 kilovolts. The grounded, which is of interest for application, is about 1300 or 14, something like that. You can see the leakage here, which is reasonable. And this is measured at 0 volt. So very important. So it's a true normally off. And the nice feature of this buffer is the breakdown field. For lateral devices, this is really, really high value. May look not that high because people think about this more than 3 megawatt per centimeter theoretical value, but nobody is using 3 megawatt per. It's not accessible, let's say. So above 2 megawatt per centimeter, these are very nice value for gallium nitride. So that's something we could see at the bias of 0 volt and giving you some pretty nice breakdown voltage. And again, very interesting is to verify again this substrate length with this normally off. This is 500 volt, kilovolt, and well above 1 kilovolt. Hysteresis is not appearing. So that has been published quite recently, by the way. So this is around. So you can get low trapping at high bias with lateral device if you control it. So of course there's a missing part here because that's not a full device. I mean, it is full device, but you also, this is just the buffer assessments. We have to be very transparent here. So this is not the on resistance, dynamic on resistance, because then at this bias, you also have to control, let's say, the current collapse from the surface at the technology level and use the right passivation. So this is just the buffer, but at least it shows you that the material itself can allow, above 1 kilovolt low trapping effects. Okay, another approach I want to share with you here is so the idea we had like 10, 15 years ago was to replace this silicon. So now ultra-wide bandgap are coming up, many people are working on that. So it was quite untypical 10 to 15 years ago. So we say, why don't we just replace the silicon by something else here? Okay, knowing that you deplete all the way down to the substrate. So you want to remove the substrate locally. Why locally? Because if you remove everything, it's difficult. Even if you bond nicely for large, especially for large wafer diameter, the strain is dominant. So the way we did it at that time is just to remove it locally. So just around the device, as you can, this is a small lab PCM device, a larger one here. So basically you have like 200 micron away, and all around, this is the backside, and there's no silicon anymore. So we just remove around the device backside all the silicon. And this can be done, Bosch has shown that now, they can do that, industry compatible, let's say, the large wafer diameter. We're very happy to see that. So these were small coupons, as we can do here in our lab, but that works also in a larger scale, okay, that you will hear about in future talks. So in our case here, we replace with aluminum nitride. That's the widest known free nitride bandgap. Obviously, this aluminum nitride is deposited at rather low temperature. Keep in mind you have all the devices processed already. So you want to be compatible with the front side here. So this is a 300 degrees C deposition, quite thick, 15 micron, because you want also to fill in the side walls. And that works, actually. And if you look at, you could imagine that this aluminum nitride, looking at its how it looks like here, that is pretty poor. But aluminum nitride is amazing. Even a poor one provides you 4 megawatt per centimeter. If it's a good one, it goes to 10, 12. But the poor, low temperature one is still way above gallium nitride and silicon carbide. That's really an amazing material. And of course, thermal conductivity is not good. So I'm not talking about that here. These are columns, but that was just to focus on the breakdown. And this worked pretty nicely. So this SD was with us a few years ago. She's with Yole now, by the way. And this is the reference device. Another nice thing of this work is this is done on the same wafer. So there's no technology variation, epi variation. So they measure the devices in the same sample. So you have with and without local substrate removal. So this is how it looks like. It's still, a kilovolt device here, or at least that is working not too bad at 600 volt. The leakage is 1 microamps per millimeter, so that's pretty low. And if you apply this process, the aluminum nitride just block all the voltage, and you end up with multiple kilovolts. So that time it was fun to compare to state of the art, because obviously it's kind of cheating because we just get rid of the main problem, which is the silicon, and those people, of course, are using GaN and silicon. So I'm not sure it's fair to compare that, but it's fun. And you see also how the device looks like at low bias. There's no variation here. Okay, so we then been challenged in an EU project. This was called INREL. A couple of friends here, people working on this project, so Christophe included there. So the idea was to say, okay, that works, but can you do that on larger scale? So we kind of tried to enlarge to optimize the large area substrate removal. So we went to multiple centimeter size here. You can see some large square, fully removed silicon, and still alive. So that works pretty nicely. And these are some on-semi devices here. So from the company, these are very large devices in terms of gate width. So this has been delivered by Peter, by the way, at that time. So there was a nice. So this was some initial normally. So this was I have to mention that this was under development at onsemi. So there was some first initial generation of normally. Of course, this has been significantly improved afterwards, but this was some few years ago. And you can see that the device we got here at 0 volt bias, so true normally off, we could see the enhancement clearly of the breakdown voltage. So this could be applied to large devices. And to prove that it's large devices, you want to use the on state. So this was about 13 ampere, got it here, amps devices. So you can see the thermal penalty. So that's why the on current here is much lower here. You still have, cannot see here, but I think it's, close to 10 amps, 9. There is a drop. The thermal penalty actually is quite severe, but you can still generate large current, higher voltage with this approach here. And more interesting is what has been done on the same devices that we delivered to University of Padova, a group. So they do nicely this pipe gating here. So these are devices GaN on silicon without local substrate removal. So what you see is a highly expected feature here. So you increase the bulk, the substrate bias of the pipe gating. So this is basically you stress for 10 seconds and then you monitor the recovery for 2 minutes. Okay, so that's what they do here for 2 minutes. So you have the current over time. So for low bias, you see that there's low trapping. And if you increase the bias, let's say beyond 600 volts, then you start to activate traps, which is kind of expected for this buffer. But for the same device, with the local substrate, we couldn't see that. That was really, really interesting. Fortunately, we didn't really follow up on that. That's what it is. We were busy enough, but we could see an outstanding reduction, and that indicates you that most of the trapping occurs at the aluminum nitride nucleation layer and silicon substrate interface. That's where really most of the trapping see. Otherwise, we couldn't observe this mix here. Okay. So, what's the situation today? So, there are many companies now that have qualified lateral GaN power switch up to 650 volts. So, the market penetration is something else. For the moment, it's silicon carbide, but the devices are existing. They are there. They are super reliable. I'm not going to mention companies. There are many. But you know most of them. And also an interesting point is that there's larger ecosystems that are being built now. So people, the message is just that people get more and more interest in this wide bandgap, and that creates, kind of. So I took a local example here because we are in Belgium. So there's a company that just started, and yeah, there's quite some excitement here. Let me check time. Oh, that's fine. Okay, I move to the let's say what's next for switching transistors, new device design. Okay, so these are very nice devices, but obviously there are some issues, and that's one of the reasons, those hands, especially at 650 volt, they are not covering the market like silicon carbide is doing. And one of the reasons is of course, people, especially like us at the academic level, we always underestimate cost or market acceptance, things like that. And that's actually based on facts, because one of the key things is if you want to increase the voltage, you have to increase the gate drain distance here, and also the current, by the way. Okay, so you end up with larger and larger devices. You need derating, and you need severe derating for these devices. So if you want to work at 650 volt, you need devices way beyond 1 kilovolt. So you need to over-design. So these devices, at the end of the day, are pretty large as compared to the contenders, let's say, the competition. And so that's a problem of size, and the other main problem is absence of avalanche. So you cannot get avalanche. That's a strong statement, that's a bold statement, but I think as long as you have an electric field peak here, there's no way to get avalanche. I don't think so. So this will be always, limited by the electric field in this case. So these are, as I mentioned here, these are several issues to market penetration. Of course, I'm happy to exchange on that. If people have other thoughts, that would be great. But that's what we observe here. And again, oversized devices, reduced acceptance from end user. 5 minutes? I'm done? Really? I thought I have more time. Oh, I'm sorry. So I'm too slow. So I'm just getting faster here. I'm really sorry. Okay, so this is not the case for vertical, on paper at least, because for vertical, the breakdown depends on the drift layer thickness, so you don't need to increase the fingerprint here, the footprint, and as silicon carbide, and silicon technology devices remain small for high voltage, and on paper you should have avalanche because there is no real strong peak somewhere in the device if you manage edge termination and quality of the layers. Sorry. Yeah, I'm not going to detail anyway this part here because this will be nicely described tomorrow, I think, by Christian Huber from Bosch, who's here. So this is the very nice YESvGaN project that will be described. So I just almost skip here. I just wanted to show you some initial results from our side that will be probably further discussed. So it's just one slide here to show you that we start working. So you see the idea. We use the local substrate removal, but to get access to the N+ fully vertical device here. Okay, so that's the same technology that I showed for lateral, but applied to vertical. And in the front side, there's nothing really special. You can use any feature, whatever. So just to show you that the progress of this project is pretty satisfactory. We've been developing, for example, large area substrate removal. In this case, you also need to etch all the buffer layers, not just the substrate. So it's about 2 micron plus that you need to etch further. So we implemented some TLMs by laser writing here, and that allowed us to find, let's say, significantly optimize, the contact resistance, the backside. This was not trivial. I won't go into detail here. We thought it was easy. It was not that easy. But with this TLMs, with this approach, we could nicely optimize. You can see the results here So you have basically no impact of this contact resistance on the on resistance overall, okay? And we got some first devices. These are just pin diodes, but it's not too bad. That allows you to look at many things. So there's some very nice epi layers from Siltronic. Alexandra is around. So these are 800 volt pin diodes with very low on resistance, with about 10th of million centimeter square. These are state-of-the-art pin diodes with pretty nice figure of merit here. This will be presented soon. And something I cannot show you, this will be published soon also, but that's not released yet, is these GaN on silicon devices show avalanche breakdown. That's new, that's brought by this very nice YESvGaN project, this nice collaboration with all the partners. But again, that will be further described tomorrow. I think I don't have really much time for the rest. I'm really sorry, but I just go fast few slides more. So you have a bunch of material here. I don't have time to go through coming up. One example is aluminum nitride. So I'm not talking about gallium oxide, which is as interesting as this one. This is long-term exploratory materials, so it's pure research so far, which is less the case for vertical, which is happening on GaN bulk, and also now on GaN on silicon with what we are doing. So the interest of aluminum nitride is even wider bandgap, even wider, even larger, electric field strength. I'll just go very quickly here, just to show you the interest of the aluminum nitride platform. If you grow a very thin, simple HEMT on aluminum nitride versus silicon, in this case, we have a thick GaN versus a much thinner one, and a one on silicon. So this is very thin, so you expect low breakdown voltage. So this is just the buffer breakdown. So the buffer breakdown on silicon obviously is extremely low because you are breaking down not immediately, but almost several tenths of volt on silicon. This is very thin. And the breakdown on aluminum nitride is endless. Actually, this is wrong. This is the limit of the liquid. You can see the liquid, the probe here. And actually, it's not the real breakdown of the material. This is really the liquid which cannot withstand, such. We are talking about 6, 7, 8 kilovolts. Okay. Just quickly here, this is the transistor breakdown. An interesting point is if you use thick gallium nitride, you suffer from the gallium nitride actually here. I will explain you here quickly. And if you make the gallium nitride thinner, you drastically increase the breakdown. This is very easy to understand. That's the silicon transistor, thin hand on silicon. You see the punch through, so the gate leakage is low, and you have punch through all through the silicon here. Okay? And if you do that on aluminum nitride, ID is equal to IG, no punch through, and the breakdown is not that high because you are still suffering or peaking in the gallium nitride. So if you make it thinner, that's the same guy, thick gallium nitride. And if you make it thinner, you drastically increase because you are confining the electron much better and depleting in the aluminum nitride more and more. So when you see that, you say, we don't want to use gallium nitride anymore. You want to use like AlGaN as a channel because you still need a difference in the band conduction. And that's what we did. I just go quickly. Instead of GaN, this is AlGaN, 50%, it's pretty high, on the aluminum nitride platform. So, okay, here is a sapphire. It's just for resources reason, we couldn't have a bulk gallium nitride, but still aluminum nitride sputtered on sapphire. So with regrown aluminum nitride. And just quickly, from buffer point of view, obviously it's very high. You can see the red one is almost a kilovolt with less than 2 micron distance. That's not something you can get with GaN. Okay, that's just a buffer, aluminum nitride. So these are the devices. Good switching. Breakdown is about 4 kilovolt in this case, so you get it for free. Obviously, if you look at the on-state, it looks very bad. That's the challenge for these devices. When you have high aluminum content structure, the contacts become very, very difficult, but we've worked on that. And we used, in this case, I don't have time to show, but we used regrowth contacts by MBE. You can argue it's expensive, but at least it's just to show that things are possible. We drastically improve the on-state behavior on this high aluminum content while keeping this 4 kilovolt breakdown. So that's interesting. So then you can say, how can you compete with that, with gallium nitride? I think the area for that is the temperature, is the harsh environment. So this should be used for niche, harsh environment applications. Because if you look at the temperature dependence on that, this has nothing to do with even silicon carbide. I mean, the people forget that the gap provides you also the independence on the temperature behavior. And that's what you see here. I mean, you can go to 200 degrees C. You have almost no change in the on state, in the off state. This has been measured by partners, not our results. So, you know, that has been verified elsewhere. So I think that's really a strength and asset of this technology. And I just conclude, I'm sorry, Christoph, about the time. It's a bit too long, so I'll just go through quickly. I've shown, you know, some basics about GaN, lateral FETs with different buffer engineering. So many things have been solved. Of course, we have qualified devices here. So great variety of normally off. There's not one solution. The P-GaN is a little bit dominant, but there are some others. So there's obviously a unique potential for low voltage. We can see that for high voltage. That's a question with lateral because of this absence of avalanche and device size. So probably silicon carbide is preferred today. But there are some novel GaN power devices. And again, I'm not talking about GaN on GaN, but this can be done on silicon. That's hopefully what this initial YESvGaN project will show at the end of the day is you can get nice, let's say, kilovolt class GaN on silicon, fully vertical, and on the horizon, new ultra-wide bandgap materials, such as the one I showed, aluminum nitride. There's also gallium oxide coming up. And I will help industry people because they are all looking for some fresh new people. So I do your job. You should pay me, by the way. So this time for opportunity, really. But it's also our case. I mean, we're looking for students, postdocs, always. And there's a real hype now. I think you can all feel it. If you have choose to young people, if you choose this topic, I think you did the right choice. So the message here is that these huge topics, multidisciplinary research. I think academic need to. It's not always easy, you know, to make academic people with industry, but that's getting better, and we need fresh and new people. So, yeah, thank you for your attention.